All right, we are ready for our next reaction in Unit 9, aldol condensation. And we'll also look at another variation of the aldol, which is an intramolecular aldol. Before we actually get to this reaction, why don't we do a little bit of a review. In the previous video, which was the first video for Unit 9, 09A50, we looked at reaction 9A, which was just an aldol reaction. And let's test ourselves. Let me give you a aldehyde or ketone that we had not looked at in the previous video. What about this one here? An aldehyde, and let's do that one. Add a base, typically an oxide base like sodium hydroxide or sodium ethoxide. Oops. NaOET. And we do need a proton source, and you're typically going to dissolve your base in the solvent that looks just like the base except neutral. That would be ethanol. Okay, well, let's do a self-assessment. Give me the product. You're going to pause the video, and then when you're done drawing your product, unpause the video and follow how I would do this problem as quickly as possible, pretending that it's on an exam or quiz. Okay, go ahead and pause. All right. What I would do is I would identify the alpha carbon and pretend, even though I don't typically draw the mechanism with the anion at the alpha, I typically draw it at the oxygen, but just pretend it's there. And I have to visualize it attacking another one of itself in the neutral form. And you're going to attack this dot right here. Okay, the way I draw the product is I am going to try to get that alpha carbon to attack towards the upper right hand side. So it's going to attack to the northeast. And let me draw the rest of the molecule. Don't forget that. It is a total of 5 carbons. 1, 2, 3, 4, 5. It's going to attack this green molecule at the dot. And you should recall that the carbonyl group of the aldehyde or ketone that's attacked becomes an OH. You just have to copy everything that's attached to the dot. And I have this. There should be a total of 10 carbons, 5 plus 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Also, if you do your Greek lettering with this being alpha, staying alpha, and this becoming beta, you do have a beta hydroxy, and in this case, aldehyde. And that's a good check to see if you did the aldol correctly. Okay. What about this aldol condensation? What is condensation? I have condensation actually on my glass. It was a glass of it's a glass of ice water, and not vapor, but little droplets of water are forming on the sides. It's a pretty humid day right now. Well, with aldol condensation, you are creating water vapor. Same thing. Where's that water coming from? It's coming from this OH and most often the hydrogen that's on this alpha carbon. Okay. Let me show you that reaction. Reaction 9B, aldol condensation. And I'll go over the mechanism for aldol condensation. It will give us a good opportunity to do the mechanism for the aldol, because to get to the aldol condensation product, you actually have to go through the aldol product. Right? This is the aldol product. The beta hydroxyaldehyde. Okay. Let me give us a challenge. Let's make it a ketone. You might have used this ketone before, but that's okay. Actually, let's use this ketone. Okay. What's the difference between an aldol reaction and an aldol condensation in terms of its conditions? We're still going to use a base. Okay. We're still going to give ourselves a proton source, right, to protonate that oxygen. But now to cause the dehydration, all we have to do is add heat. And that's it. So without heat, you do the regular aldol. With heat, you do what we're about to do, the aldol condensation. I don't expect to see the intermediate on an exam. So maybe on a scratch sheet of paper, though, if I'm still unsure of what to do here, let me draw the Aldol product first. Because the Aldol condensation is coming from the Aldol product. Now I just want to make sure that I have the right number of carbons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I tack to the upper right, the northeast. I make that an OH. And on that dot, we have 2 propyl groups. 1, 2, 3. 1, 2, 3. There should be 12 carbons, right? Well, no, there should be 14. 1, 2, 3, 4, 5, 6, 7 times 2 is 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Brackets because it's an intermediate. This is your aldol intermediate now. It's not the final product because we're adding heat. And when you do heat, if you can, you're going to make the double bond between the alpha and the beta. Right, this is your beta hydroxy ketone. You're going to make the double bond between the alpha and the beta. And if you have a choice between cis and trans, you're going to make the more stable trans, but because we have 2 of the same groups, there is no cis and trans. Your final product for this reaction is this. Double bond between the alpha and beta. There's no more OH. Remember, we are removing H2O, removing water to make the condensation. But we still have 1, 2, 3. Okay, we should still have 14 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I forgot the other propyl group. Yikes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. If you want, you can mark where your alpha is and your beta. And we did kick out water. Okay, normally you don't draw the water, but just to emphasize that we did do a dehydration, right? This is a dehydration. Now, the clue that we had an aldol product, or the check, is that you made a beta hydroxyaldehyde. What is the clue for the aldol condensation? Aldol condensation. You make, aldol condensation. Let me zoom out. Okay. You make called an alpha, comma, beta, dash, unsaturated. And in this case, it's an unsaturated ketone. Unsaturated means that you have a carbon-carbon double bond or a carbon-carbon triple bond, and that double bond right there causes this molecule to be called unsaturated between the alpha and the beta carbon. Why do they use the term saturated or unsaturated? Because, for instance, look at this carbon here, okay? This carbon-carbon bond is a single bond, and you have as many hydrogens as you can fit for these 2 carbons, 4 hydrogens. That means that this molecule or this carbon-carbon bond is saturated with hydrogen. But you notice that when we make a double bond here, we lose 2 hydrogens, so now it becomes unsaturated. Okay? Now there are a couple things before we get to the mechanism about this aldol condensation that you may be wondering. Pretend that we had this molecule here, and let's make it an alcohol. So I'll put my thumb over the carbonyl group. If I ask you, my nose is itchy. If I ask you, do a dehydration, well, remember you can make several different alkenes usually, because we have several different carbons next to this carbon here. Now the Greek lettering had changed because we normally would call it an alpha carbon if it was just an alcohol. Okay, but remember it's called beta hydrogen elimination. You eliminate the hydrogen next door to the carbon that's attached to the oxygen. Don't worry about that. But you should recall that if you dehydrate this molecule, let me cover the rest of the molecule. If I dehydrate this molecule, you have chances of multiple alkenes, okay, depending on which beta hydrogen you remove. Okay, or let me just cover that, depending on which beta hydrogen you remove. Same thing here. Why didn't I make the double bond to the right? Why didn't I make the double bond going up? Why did I make it towards the alpha carbon? Because this is called a conjugated system, or conjugated, you could call it enone, or alkene ketone. But even if this was an aldehyde, you would still call it an enone, a conjugated enone. Conjugated means that you just alternate, double bond, single bond, double bond. Okay, we could have extended conjugation if we had a double bond right here, but you're alternating, double bond, single bond, double bond. So those two double bonds are conjugated, or you could even say the pi bonds are conjugated. I'm not going to get into it in this unit, but in a future unit, I believe possibly unit 11, we are going to discuss why conjugated systems are more stable, inherently more stable than non-conjugated systems. Okay, so when you have an opportunity to make the double bond closer to the carbonyl group, take that opportunity. Why do we have an opportunity? Because there's a hydrogen right there. Okay. So conjugated enones are stable than non-conjugated. Than non-conjugated. Yikes, what's going on with my handwriting? Let's do the mechanism. Am I going to fit all the mechanism on this page? Let me just double check. Okay, I'm going to try to fit it on this page. It's going to be a little bit cramped, and I'm going to draw a little bit smaller, but it should fit. Because we're going to make the aldol first, and then get to the aldol condensation. This is a good review to how to make an aldol. Okay. Find the alpha carbon. Remember, when you have a carbonyl group, the alpha carbon is not the carbonyl carbon, but the one next to it. It's symmetrical, so it doesn't matter which alpha carbon I look at or abstract. And I have OET, ethoxide. That's my base. I'm going to grab this hydrogen. And do you recall that I don't typically draw the anion on the carbon? I draw the anion on the oxygen. So you're going to make a double bond there, and you're going to push up the pi bond to that oxygen. Now, there are some websites and there are some professors who say go ahead and put the anion on the carbon. It is essentially the same thing because those are resonance structures. Whether you put the anion here and make sort of the enol, or the enolate this way, or whether you stop with this green arrow and you put the lone pair on the actual carbon. Doesn't matter in terms of mechanism, but I prefer it this way. Okay, we did create ethanol, but that's just a side product. So what's the key? The key is attacking. Like, what do you attack? You attack another one of itself, and how am I going to draw that? Oh, it doesn't actually matter because it's symmetrical. Okay. Now, you are going to attach to the alpha carbon. Where's my alpha carbon? It's this one right here. Okay. You're not going to attach to the oxygen. And I should explain that if I have time at the end of this video. So you make the double bond, you tack the dot. All we're doing is doing the Aldol mechanism that we learned in the previous video. Now, the way we draw this, I picked a pretty big molecule. It's not making it easy. We made this bond here. You have O minus. Yeah, I picked a big molecule. That should be it, right? You made the bond between this alpha. Where do I want to put it? I'll put it here. The alpha and the dot. Finally, the last step, we're going to get the aldol product. And since we're working with ethanol, why don't we just take our proton from that. And we form now our aldol product. Okay, big molecule. What is it? Is it 3 steps to the aldol? 1, 2, 3. We have to create water. Now this is going to seem a little bit strange. Oh, by the way, we created a new base, right? We created a new molecule of ethoxide, which is good because we're going to use that to deprotonate and do an elimination. Elimination, dehydration, condensation, those 3 mean the same thing in this reaction. Remember that we want to try to make the double bond between the alpha and the beta so it becomes conjugated. We do have a hydrogen right here, so we could do that. Now, go ahead and copy my mechanism arrows. And I feel like a couple of you out there are going to be yelling at me. Why are you yelling at me? Because what did I tell you about OH as a leaving group? It's typically said that OH, let me just finish this. Big molecule. OH is a bad leaving group. OH is a bad leaving group. I'm trying to make sure that I copied it or I have the right number of carbons. Okay. So why did I do this? There are a couple reasons. The first reason is that we're using heat. Okay. Heat will push the reaction. So the OH now, we're giving it more energy to leave. The other thing is that we have base. Okay. And we're able to rip off this hydrogen. But the most important thing is that the reaction has a motivation to get to the dehydrated product because conjugated enones or conjugated systems or pi systems, however you want to say it, are inherently more stable than non-conjugated. So there is a thermodynamic force or thermodynamic, I want to say motivation, thermodynamic reason why this is okay, even though in previous units we said OH is the bad leaving group. In this case, you can make it leave under these conditions. Did we make the product that we want? So here's your aldol condensation product. And it looks like the same right here. Okay, that is aldol condensation. You could take any, not any aldol, but you could take most aldols and do a condensation. The rare cases where you can't do a condensation is if there's no hydrogen here or no hydrogens anywhere next door to the dot. Okay. And then again, when you have an opportunity to make the double bond towards the carbonyl group, take that opportunity, and that would be your major product. I will never ask for my students to draw the minor products, which would be the alkenes on the other carbons. Okay. All right, so this is good. On one page, we're able to get side by side an aldol reaction and an aldol condensation. What about that intramolecular aldol? This would be reaction 9C. Again, if you master the aldol reaction, the next 5 or 6 are going to be really easy because they all play off of it, play off of the regular aldol. We have an intramolecular aldol. Intra meaning within the same molecule. Like interstate is a road between states. I don't think there's such thing as intrastate, but intracellular within the same cell. Intramolecular within the same molecule. Take a look at how different the starting material looks like. I'll give us a diketone. Interesting. Because we have two ketones, we have multiple alpha carbons to deprotonate, but we also can attack within ourselves. It's an aldol reaction. So let's give us some base with a proton source, in this case now water. I'm going to say no heat for now. Okay, so yes, we're going to do an intramolecular aldol, but now that we've seen condensation, you could easily do an intramolecular aldol condensation as well. But let me show you just the plain aldol using this molecule. We have basically two types of alpha carbon. We have the alpha carbon that's green and the alpha carbon that's pink. Right, those are different. Let's analyze the green. Let's pretend that we have an anion at that carbon, like we did a deprotonation. Again, what I say is tricks to get to the product, but you know that for the mechanism, I typically don't want to put the anion there. I want to put the anion on the oxygen. And you saw how I did that. But because we have a carbonyl group in the same molecule, that carbonyl group will always be close to this anion, closer than a molecule that's not connected. So the chances of us making an intramolecular bond are good. Okay, they're good. And this, we make a 7-membered ring. How did I get 7-membered? If that carbon attacks that dot, I have 1, 2, 3, 4, 5, 6, 7 carbons in that ring. Let's take a look at the situation where we have a deprotonation at this alpha carbon, the pink one. Then I would attack this here. It's kind of a, I don't know, a nonsense question, but do you see why this alpha carbon or this anion doesn't attack this carbon? Because they're already attached. So you go for the carbonyl that's distant, or that's not attached to that alpha carbon. How many carbons would be in this ring? It's a 5-membered ring. It's a pentagon. Okay, due to bond angles, right, it's more likely that these two carbons will find each other than these two carbons. Okay. Just has to do with bond angles. You know, a 6-membered ring, once it's a chair conformation, all of those bond angles are tetrahedral, right? A 5-membered ring, it's a pentagon that has an internal angle of 108, close to 109. So due to bond angles, only make 5 and 6-membered rings when you're doing an aldol reaction. So we're choosing the pink. We're choosing the pink. If I know that I'm making a 5-membered ring, this is a trick. Okay? Don't get psyched out by everything that's attached to this molecule. Just draw your 5-membered ring and put a dot anywhere, because that dot is this dot right here. Now, if you want to go ahead and number, you can. Let's say the attacker's 1, 2, 3, 4, 5. So if this is 5 and it got attacked by 1, you know where 2, 3, and 4 are. Look what else is attached to carbon number 5. You know that when you attack a carbonyl group in an aldol reaction, right here, ultimately you're going to make the OH. Okay, this will get protonated to make the OH. So that carbonyl group, make it an OH now. It's also attached to a methyl group. Okay. See, the trick is draw your ring right away and then decorate it. Don't try to decorate it and make the ring closure at the same time. You'll get confused. Carbon number 1 is here. Look at the stuff that's not part of the ring, though. It's hanging off of the ring. So carbon number 1 is connected to this carbonyl, and that's connected to a methyl. That's your product, right? And you see that it's alpha beta. It's a beta hydroxy ketone. Good. That's what you expect when you make a aldol product. Either the beta hydroxy ketone or the beta hydroxy aldehyde. Okay. Now, just make sure you have all the carbons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Whoa, 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 whoa. 1, 2, 3, 4, 5, 6, 7, 8. 8. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay. If I had added heat, and you could add heat, really you would want to add heat here, but let's add heat and some base. Okay. Then where would the double bond occur? That's my question for you. Draw the product of this now. So we're kind of breaking up the aldol condensation into its two parts, making the aldol and then doing the condensation. But we could have easily gotten this product if we just added heat at this underneath this arrow. Okay, what is the product in this case? Pause the video, draw me the aldol condensation product, and then double check your work. Okay, it would look like this. There's one way to draw it. Still have that methyl group right there. This is your dot. We removed H2O, 2 hydrogens and an oxygen. This oxygen, this hydrogen, and the hydrogen that was here. Okay, there's a hydrogen there. Good. Alpha, beta. Alpha, beta unsaturated ketone. This is your condensation product. Alpha, beta, unsaturated. In this case, it's a ketone. Okay. Okay. At home, and I'll probably put this on the practice sheet that goes with this video, but at home, do this reaction. I'll give you a dialdehyde this time. It's still going to be symmetrical, so that makes things easier in terms of picking the correct alpha carbon to deprotonate. Let me just double check. 1, 2, 3. See, I'm checking whether a 5 or 6 membered ring is possible. And I'll give us NaOET for the base, ethanol for the proton source, and now I am asking you to heat it. So I do want the final form to be the condensation product, the one with the conjugated enone. Okay. Now there's one last thing. There's a loose end that I want to talk about, and it's fairly quick. For the enolate, you have this. You have an O minus, and your resonance is this, where the anion is now on the carbon. In terms of mechanisms, you want this one for mechanisms. But the question is, when I add an electrophile, okay, the electrophile that we've been using is just a carbonyl group. That's an E+. You could put the electrophile on the oxygen, right? That makes sense because opposites attract. Or you could do like in an aldol, put it on the alpha carbon, which is what we've been seeing all the time. So this is your aldol product. The reason for that is, again, for the mechanism, this is the major contributor, the major resonance contributor. So I like drawing the mechanism through the O minus. But in terms of the product, we're not alkylating, or we're not alkylating, we're not attaching anything to the oxygen, right? We're always attaching something to the alpha carbon. That's because when you look at the final product, a C double bond oxygen is stronger, more stable than what? Than a CC double bond. So thermodynamically, you want, and there are other reasons if you read the textbook, but the one that I remember is that thermodynamically, you want to make the carbon-oxygen double bond. And that's why we do, in our mechanisms, reform that carbon, where is it? Right here. We reform the carbon-oxygen double bond. Okay, oops. We reformed that and it's right here now. Okay. That's why we do all of our attacking using the carbon and not the oxygen. So the thing is, how do I resolve this? Because it looks like they're coming from two different resonance structures. Well, you saw how I do it. You remake the double bond, right? And then you, let me draw an arrow this way. And then you attack your carbonyl group. Okay, in this case, we'll make it E. That set of arrows will give you this molecule here. Okay. All right, next video, we're going to move on. There are more aldol type reactions, so make sure you brush up on aldol condensation, this intramolecular aldol, and this take-home problem, and you'll be set for the next two, which are still aldol type of reactions.